Flexible couplings are a passion of mine. I love taking readings on couplings. It's such an easy thing to do, and you can get some immediate wins. And it really takes away the need to intrusively inspect things that don't need to be inspected. So one of our customers, every shutdown would pick a number of couplings, grid-based flexible couplings that they would open up and inspect because they had work orders for it. And 9 times out of 10, there'd be nothing wrong with these couplings. So they'd spend 2 hours, removing guards, taking things apart, inspecting, and then putting it all back together and replacing a guard. And when you're doing this for absolutely no reason, you're taking up valuable time on your prime shutdown hours. You're taking resources to perform unnecessary tasks when those individuals could be put to work doing other more necessary tasks. And the way we do this is it's a very quick 5 to 10 second listen with a flexible sensor. So flex sensor is my kind of sensor of choice. You just need to find a gap in and around the guarding, point it up towards the coupling and take a listen. And really what you're listening for is white noise. If there's no issues, nothing going on, it's going to be very smooth, very quiet. So this is what a good coupling sounds like. So again, play this, very quiet, very smooth. Versus, a coupling that obviously needs some attention. Very easy to tell the difference. A good coupling is just going to be smooth, white noise, nothing going on. Once you start to hear, fluttering, impacting, whooshing, these are all indicators of wear or damage or lack of lubrication to your couplings, depending on the style of coupling you're using. You can also see it in the FFT as well. You'll see it at running speed with harmonics. And it's kind of an indicator of looseness as well. So you're getting that looseness pattern, harmonics at 1 times running speed. Now here was the evidence on this one. So you see oxidation here. It's just worn out, starting to crack. It just needed to be, the grid needed to be replaced. It needed to be cleaned out and taken care of. Again, you can see in the actual coupling itself. Here's an example of one that was actually broken. Again, you've got that repetitive impacting kind of fluttering type noise going on. Many more indicators of running speed harmonics through the FFT, very clean, picks it up very nicely. And then we actually had a broken grid. And when a grid is broken, that is going to reduce the ability to transfer power from the motor to whatever it's driving. And the thing's just going to get worse over time, to the point where, the motor will continue to run, but once power can't be transferred, whatever you're trying to drive is just going to sit there idle. So we've actually had cases where people have gone out to do or to take readings, and they'll take a reading on the motor, they'll take a reading on the pump, for example, and they come back and we look at the data and you can see clearly that the motor is running, but the dB values or the readings we're getting from the pump were virtually next to nothing. And, so we said, okay, can you go out and actually take a look and look at the coupling and make sure that this pump that is supposed to be running is running? Because from the data we're seeing, it's not. So when they went back out there to inspect, the coupling had broken. So the motor was running. So anyone casually walking